The topic of today's lecture is linear independence. This notion is one of the most fundamental notions in linear algebra. Let us look at linear combinations of vectors. A linear combination C1 V1 plus C2 V2 plus Cn Vn is called trivial if all coefficients Ci's, so C1, C2, and Cn are all equal to 0. And of course, a trivial linear combination is equal to a 0 vector. So this means that if we take 0 times V1 plus dot 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 plus 0 times Vn, so of course the result is a 0 vector. Now the question that we are asking is it possible to obtain a 0 vector as a linear combination of V1 through Vn, which is not trivial? So this means that can we get a 0 vector as a linear combination with not all coefficients being 0? So then this motivates a definition. So a set of vectors, so V1 through Vn, is called linearly dependent if there exists a linear combination of these vectors C1 V1 plus Cn Vn, which is equal to a 0 vector. But not all coefficients are 0. So in other words, that a set of vectors is called linearly dependent if there exists a non-trivial linear combination of these vectors, which is equal to a 0 vector. Right? So in this non-trivial linear combination, some of the coefficients are allowed to be 0. What's important is that not all of them are equal to 0. And now we say that a set of vectors V1 through Vn is called linearly independent if it is not linearly dependent. So equivalently, this can be formulated in the following way. So this set is linearly independent if only its trivial linear combination is equal to the zero vector. Now, what's important for us is the definition of linear independence, but it's easier to formulate what does it mean for vectors to be linearly dependent. And so this creates a complication that we'll also often will have to use in proofs. So when we want to prove that something is linearly independent, we essentially will have to prove that something is not linearly dependent. Let us try to understand the concept of linear independence better. What is it about? Well, linear independence is about the following vector equation. So we're looking at C1v1 plus C2v2 plus Cn/Vn being equal to a zero vector. So we treat this as a vector equation. And if this equation has the only solution C1, C2, and all coefficients being 0, then this set of vectors is linearly independent. On the other hand, so if there is a solution with not all Ci being 0, then this set of vectors is linearly dependent. Now let us consider some small examples. So let's ask the following question. When is the set that consists of one vector linearly dependent or independent? So the corresponding vector equation is C times V is equal to 0. And we are interested in finding whether this vector equation has solutions with the non-zero values of C. So what we see is that if C here is not equal to 0, then we can, well, C is an element of a field which is non-zero, it's invertible, then we get C inverse times CV is equal to C inverse times 0. And then this implies that 1 times V is equal to the 0 vector, or this implies that V is equal to 0 vector. So what we see is that if this vector equation has a solution with the non-zero values of C, then this implies that the vector is equal to 0. And conversely, if a vector is equal to 0, then obviously this equation will have a non-zero solution because 1 times 0 vector is equal to 0. So the conclusion here is the following. So that if we take a set that consists of a 0 vector, then this set is linearly dependent. And if we take one vector which is not equal to 0 vector, then this set of vectors is linearly independent. So for one vector, we understand linear dependence and independence. So if this vector is a zero vector, then this set is linearly dependent. If this vector is non-zero, then the set is linearly independent. Now, let us look at the situation when our set contains two vectors. And let's ask the question. So when the set of two vectors v and w is linearly dependent or independent. Now, suppose it is linearly dependent, because linear dependency is easier to understand than linear independency. Suppose this set is linearly dependent. By definition, this means that there exist two scalars, C1 and C2, where either C1 is not equal to 0 or C2 is not equal to 0, such that the corresponding linear combination C1v plus C2w is equal to a zero vector. But okay, so here the situation is a little bit symmetric. So we have C1 and C2. So let's assume C1 is not equal to 0. So then we can write that C1v is equal to minus C2w. Right? So we can bring this term to the other side. And then, since C1 is non-zero, and this is an element of a field, so we can multiply both sides by the inverse of C1. So then we get C1 inverse times C1v is equal to minus C1 inverse times C2w. And so this tells us that v is k times w, where k is equal to minus C1 inverse times C2. And so what we conclude here is that if these two vectors are linearly dependent, then one of these vectors is a multiple of another. So we get that so if this set is linearly dependent, then this means that one of the vectors is a constant multiple of the other. And in fact, these two conditions are equivalent. So if one of the vectors is a constant multiple of the other, then these two vectors are linearly dependent. So let's see this. So suppose v is k times w. So then this implies that 1 times v minus k times w is equal to 0. But this becomes a non-trivial linear combination. It's non-trivial because the first coefficient here is equal to 1, so it's non-zero. Right? And so what this shows is that, well, if this set is linearly dependent, then one of the vectors is a multiple of the other. And here we see the converse. So if one of the vectors is a multiple of another, then that there exists a non-trivial linear combination of these two vectors, which is equal to the zero vector. So let us make some drawings of linearly independent vectors. Right? So for a single vector, all we want that this vector is non-zero. For a pair of vectors, so we require that they must not be multiples of each other. So this we should have two vectors that go in different directions. Right? So this is linear independence of two vectors. And of course, if one of the vectors is 0, then it already becomes a multiple of the other vector. So this would be linearly dependent. Now, for three vectors, the situation is a little bit more complicated. Now, for example, let's ask the following question. So suppose I take three vectors on a plane. So this vector is 1, 0. Then this vector is 0, 1. And I'll take the third vector, -1, -1. Right? And I will ask, is this linearly independent? Right? So here, so three vectors are non-zero, and none of them is a multiple of another vector. So yet, what we get is that the answer is that these three vectors are linearly dependent. And we can see this in the following way. So if I take 1 times 1, 0, plus 1 times 0, 1, plus 1 times -1, -1, right? So what is it equal to? So here, if we calculate everything, then we see that this is equal to 0, 0. So what we have is, on the left, we have a linear combination of these three vectors, and this linear combination is equal to a 0 vector. And this linear combination is non-trivial, because not all coefficients are equal to 0. So this means that we were able to construct a non-trivial linear combination of these three vectors that is equal to a 0 vector. So the conclusion is that this set of three vectors is linearly dependent. Now, so it turns out that to get three linearly independent vectors, we need to go to a three-dimensional space. And so in a three-dimensional space, so three vectors are linearly independent if they form a tetrahedron. Right? So we have tetrahedron here. Then they will be linearly independent. So in other words, so we require that these three endpoints of these vectors and their common initial point do not lie in the same plane. Right? So these 4 points are not in one plane. And we can appreciate that we actually have seen the definition of linear independence when we discussed Euclidean geometry on a plane and in three-dimensional space. Right? Only we did not use this term. So I kind of encourage you to revisit your notes on this subject and see where did we have the definition of linear independence. Let us discuss some basic properties of linear independence. We formulate the following theorem. So let S being the following set of vectors. So V1, V2, up to Vk be a subset of a larger set of vectors of the set R, which is V1, V2, up to Vk, and then Vk plus 1, up to Vn. So this is our setup. We have a smaller set of vectors and a larger set of vectors. So what we say that if R is linearly independent, then S is linearly independent. So in other words, a subset of a linearly independent set is itself linearly independent. So if we have a linearly independent set, then we can take a smaller part of it, and it still is going to be linearly independent. Now, so here, so in order to prove this, right, so we are going to take the contrapositive of this statement, right? And so here, so let me recall. So if we have a statement, some A implies B, then contrapositive statement is not B implies not A. So this is negation, right? And and what we have is that a statement, so A implies B, and a statement not B implies not A, are logically equivalent. So indeed, suppose A implies B, and suppose we know that B fails. Then A cannot be true, because if A is true, then B is true, but we know that B is false. So this means that if we have this, then not B will imply not A. But this works in the opposite direction as well. Suppose we know that not B implies not A, and suppose we know that A is true, then B cannot be false, because if B is false, then A is false, and we know that we're supposing that A is true. So this means that if we have this, then the truthness of A will imply the truthness of B. And what we showed here is that if we assume this statement, then we get its contrapositive, and if we assume the contrapositive, then we get this statement. So proving A implies B is equivalent to proving not B implies not A. And why do we want to switch to a contrapositive here? Why not proving this? It's because it's easier to formulate what it means for a set to be linearly dependent than to formulate what it means for a set to be linearly independent. So it makes sense here to switch to negations for us. Now, let us write down what's the contrapositive to this statement. So here, our statement A is R is linearly independent. So this is A. And our statement B is S is linearly independent. So contrapositive means negation of B implies negations of A. But negation of B becomes if S is linearly dependent, then the larger set R is linearly dependent. So now, instead of proving that a subset of a linearly independent set is linearly independent, we're actually proving that if we take a linearly dependent set and enlarge it, then the result is still linearly dependent. And because this is a contrapositive of the statement of this theorem, so this is logically equivalent to what we need to prove. Now, let us now prove this statement. So how do we prove that? So we have if something, then something. So what we do is we assume the assumption of this if statement. So suppose the set S is linearly dependent. So what does it mean? So this means that there exists constants C1 up to ck, right? So this is our set S, not all 0, such that the corresponding linear combination is equal to 0. So C1 V1 plus CK VK is equal to the 0 vector. But then we can write a linear combination of a larger set, which is equal to a 0 vector, in the following way. So C1 V1 plus CK VK plus 0 times VK plus 1 plus dot dot dot, put all zeros here, 0 times Vn. So this is still going to be 0 vector because we did not change the left-hand side. And now this became a linear combination of a larger set of vectors, R, right? And in this linear combination, some of the coefficients are equal to 0, but we know that not all coefficients are equal to 0 because not all of the first k coefficients here are 0. So this tells us that this is a non-trivial linear combination which is equal to a 0 vector. And this implies that this larger set R is linearly dependent. And so now it's useful to kind of remember actually both statements. So here we get that if we have a larger set which is linearly independent, then it's any smaller subset is linearly independent as well. And if we already have a linearly dependent set and try to enlarge it, the result is still going to be linearly dependent. Now, in particular, so let's apply this to sets with 1 or 2 vectors, right? So we know that a set with a 0 vector, so if we have a set with a 0 vector, so this is linearly dependent. And then if we enlarge this set, so if we have any set that contains a 0 vector, then by this theorem, it's automatically linearly dependent, right? So if a set contains a 0 vector, then because 0 vector is a linearly dependent set, then any larger set will also be linearly dependent. So any set that contains a 0 vector is linearly dependent. In the same way, we see that a linearly independent set, say V1 through Vn, cannot contain a pair of proportional vectors. Because we know that if we take 2 vectors where one is a scalar multiple of another, then this set of 2 vectors is linearly dependent. And since we know that a subset of linearly independent set is linearly independent, so this means that we cannot have 2 vectors inside that are multiples of each other. Our next theorem is the following. So a set V1 through Vn is linearly dependent if and only if one of the vectors is a linear combination of the others. Now, this theorem is consistent with what we said about linear dependence for pairs of vectors. Because if we apply this theorem to a pair of vectors, then we get that a set of two vectors is linearly dependent if and only if one of the vectors is a constant multiple of the other, right? So because there will be only one other vector left. So let's give a proof of this theorem. So in this theorem, we have if and only if statement. So we have a part A and a part B. Well, a statement A and a statement B. And we want to prove that A happens if and only if B happens. So in order to prove this thing, so there are two things to prove. We need to prove that A implies B, and the second thing, we need to prove that B implies A. So this is what we're going to do. So now our first part is that A implies B. So that if a set is linearly dependent, then one of the vectors is a linear combination of the others. So how do we prove this? So we assume that our set, so V1 through Vn, is linearly dependent. So what does it mean? So this means that there exist scalars C1 through Cn, not all zero, such that C1 V1 plus Cn Vn is equal to a zero vector, right? Now, so here we need to prove that one of the vectors is a linear combination of the others. So it doesn't matter which one, right? So we're going to assume without loss of generality, so without loss of generality, let's assume that C1 is not equal to 0. So we know that one of these coefficients is non-zero. Okay, so let's just assume that it's the first one that's non-zero. So then we can write that C1 times V1, so we can move everything else to the other side, is equal to negative C2 V2 minus Cn Vn. And then since C1 is non-zero and C1 is an element of a field, we can take its inverse. So and then we get that C1 inverse times C1 V1 is equal to minus C1 inverse C2 V2 minus C1 inverse Cn Vn. And so then this tells us that V1 is equal to negative C1 inverse C2 V2 minus C1 inverse Cn Vn. And so what we see, so what this means is that V1 is a linear combination of the remaining vectors from V2 to Vn. Because in the right-hand side, what we have here, so that's a linear combination of the remaining vectors. And so what we proved here is that if we assume that this set is linearly dependent, then we can express one of the vectors as a linear combination of the others. Now we need to prove the converse, so that if one of the vectors is a linear combination of the others, then this set of vectors is linearly dependent. Now we are proving that B implies A. So if one of the vectors is a linear combination of the others, then this set of vectors is linearly dependent. So again, without loss of generality, so let's assume that V1 is a linear combination of the remaining vectors from V2 to Vn. So this means that V1 can be written as K2 V2 plus Kn Vn. For some scalars, K2 to Kn in our field. So then, well, basically we run this argument in the opposite direction. Let's move this to the left-hand side. So we get that V1 minus K2 V2 minus Kn Vn is equal to the 0 vector. And here I can put a factor of 1. And what we see here is we see that we've got a linear combination of V1, V2 through Vn, which is equal to a 0 vector. And this linear combination is non-trivial because the first coefficient is guaranteed to be non-zero. And so we get a non-trivial linear combination of vectors V1, V2 through Vn, which equals 0 vector. And we conclude that this set of vectors, by definition, is linearly dependent. And this concludes the proof of this theorem. So we prove that A implies B and B implies A. So now we can use this theorem to justify what we said about linear independence of 3 vectors, right? So if I have a set of 3 vectors, so what I'm not allowed is to have one vector which is a linear combination of the other 2. But if one vector is a linear combination of the other 2, then this would mean that such a vector lies in the same plane because of the parallelogram rule, right? So the third vector cannot lie in the same plane as the other pair of vectors. And so this tells us that if we want to get a linearly independent set of 3 vectors, then they should not be sitting in the same plane. So this means that they should form this tetrahedral shape. Our next theorem will give us a computational tool that will answer the following question. So how to decide when a set of vectors in Fn linearly dependent. And so the answer to this is the following theorem. So the following 3 conditions are equivalent. One, a system of linear equations ax equals 0 has the only solution x is equal to 0 vector, right? So, well, here we have a homogeneous system of linear equations. So clearly x equals 0 is a solution. And here we are saying that this system must have only this solution. 2. Columns of A are linearly independent. And 3, row echelon form of A has a pivot in every column. So what we're claiming is that these three conditions are equivalent to each other. So the proof of this theorem is based on our different interpretations or different points of view on the system of linear equations. And so what we saw is that this system of equations, so ax equals 0, is equivalent to a vector equation. So x1 times column 1 plus x2 times column 2 plus xn times column n is equal to a 0 vector, right? So this system of linear equations is equivalent to this vector equation. But then what does it mean that ax equals 0 has the only solution x equals 0? So we see that this is equivalent, that the only linear combination of the columns C1 through Cn, which is equal to a 0 vector, so is trivial. So this means that x1 and xn is equal to 0. But this is equivalent to saying that the set of columns C1 through Cn is linearly independent. So here, so what we obtain is that 1 and 2 are equivalent to each other. So saying that a system of linear equations with a 0 right-hand side has only a trivial solution x equals 0. So because of this interpretation of systems of linear equations as vector equations with columns of the matrix, we get that this is equivalent to saying that columns of this matrix are linearly independent. So now we prove that 1 and 2 are equivalent to each other. So the next step is to show that 1 and 3 are equivalent as well. So here, so how do we solve a system of linear equations? Well, we bring this matrix to row echelon form or reduced row echelon form, and then we decide which variables are free, which are leading, then we assign parameters to free variables, and we get the general solution. So what we see is, so ax equals 0 has only solution x equals 0. This happens if and only if every variable is leading. So that is, there are no free variables. And so because if we have free variables, then we get free parameters, and we can assign non-zero values to these free parameters, and we get non-zero solution. And what does it mean that every variable is leading? And so this happens if and only if there is a pivot in every column of row echelon form of A. Because so this is how we get leading variables. So leading variables are those variables that correspond to so that where the corresponding column has a pivot, right? So remember that we have a correspondence between columns of a matrix and the variables. So if a column has a pivot, then the corresponding variable is a leading variable. And so in order to have all variables to be leading, we must have a pivot in every column. And so this shows that 1 is equivalent to 3. And so we proved that 1 is equivalent to 2, 1 is equivalent to 3. And so all these three conditions become equivalent to each other. Now, using this theorem, we can answer the question that we started with. So how to decide whether given vectors v1 through vk in Fn are linearly dependent or independent, right? Well, this theorem says something only about columns of a matrix. And here we don't have a matrix, we just have vectors. What do we do? So the trick here is the following. Form a matrix A by placing given vectors v1 through vk as columns. So then once we do this, so now columns of this matrix become our vectors. And by answering the question about linear independence of the columns, we answer the question about linear independence of our vectors. And so what we do is find row echelon form of A, right? And then get the answer. So if we have, so if row echelon form of A has a pivot in every column, so then this means that this set of vectors is linearly independent. And if row echelon form of A has a column without a pivot, so then this means that this set is linearly dependent. So let me point out that this procedure is consistent with our mantra. So in the last class we said that when we want to say something about vector equations, then we should form matrices by placing these vectors as columns. And that's exactly what happens here. So linear independence is about vector equations. And so to answer this question, we have to form a matrix by placing these vectors as columns. And this is important, right? So it's important to put these vectors as columns and not as rows, because this theorem is only about the columns of A. And so we just, once we form this matrix, then we do our steps of Gaussian elimination and find the row echelon form of A, and then from this row echelon form, we see what is the answer to our question. And if we need to find actually, so if the set is linearly dependent, and if we actually need to find specific linear combination which is non-trivial and is equal to the zero vector, then the solution, non-zero solution of Ax equals 0, right? So here will give us the linear combination of the columns that is equal to the zero vector. So let us mention the following related theorem. So if a homogeneous system Ax equals 0, well, homogeneous means that it has a 0 right-hand side, has more unknowns than equations, then it has a non-trivial solution. So non-trivial meaning that there is a solution where x is not equal to 0. Right. So let's give the proof of this. So when does such a system has a non-trivial solution? So we can say that Ax equals 0 has a non-trivial solution if and only if, so we have free variables. Because if we have free variables, then we can assign arbitrary values of parameters to the free variables. So this means that we can assign non-zero values of parameters for free variables. And then this gives us a non-trivial solution of this system of linear equations. But, so what we have here is that row echelon form has at most one pivot per row. And the number of rows is equal to the number of equations. And the number of columns is equal to the number of rows. So since we have more columns than rows, so there will be a column without a pivot. Right? So because we have the number of pivots can be at most be the number of rows, because we can only have one pivot in a row. But then we have more columns than the number of rows. So this means that there will be surely a column without a pivot. And so this implies that there is a free variable. Right? So because a column without a pivot corresponds to a free variable. And this implies that there exists a non-zero solution. Of Ax is equal to 0. Right? So basically this says that, so if we have if we have a homogeneous system, right, with a 0 right-hand side, and it has 3 equations and 5 unknowns, then so this system will have a non-trivial solution, right? So what can we say about non-homogeneous systems? Suppose we have a non-homogeneous system of 3 equations with 5 unknowns. Then it is possible that such a system is simply inconsistent, right? We could have an inconsistent system with more unknowns than equations. But if it is consistent, then we know that, so remember we had a theorem that said that if we have solution set of AX equals 0, so is a subspace, then for a consistent system, solutions of AX equals B will be kind of this subspace shifted by one particular solution. So this means that if we have, say, one solution of AX equals B, and suppose we work over Rn, then so if here we have one non-zero solution, then there will be infinitely many non-zero solutions, because it's a subspace. Any multiple of a non-zero solution is again a non-zero solution. And this correspondence between solutions of AX equals B and AX equals 0 says that if we have a consistent system with 3 equations and 5 unknowns over real numbers, then it will have infinitely many solutions. So this theorem has the following corollary. Every set V1, Vk of k vectors in Fn with k greater than n is linearly dependent. So this means that if we take more vectors than the number of components in them, then this set will be automatically be dependent. So for example, 3 vectors in R2 will have to be linearly dependent. So this is what this theorem says. So let's give a proof here. So for the proof, we know that so V1 Vk is linearly dependent if and only if Ax equals 0 has a non-trivial solution with x not equal to 0, where A is formed by placing V1 through Vk as columns. Right? So this is our, not this theorem, but the previous one. And what is the size of matrix A? So A has k columns. Right? So this is how we formed it. We placed k vectors as columns. And how many rows does it have? So the number of rows is equal to the number of components in this Fn, right? So A has n rows. And what we have is that k is strictly greater than n. But when we look at this system, Ax equals 0. So the number of columns is the number of unknowns. So this is number of unknowns in Ax equals 0. And the number of rows is equal to the number of equations. And now we apply this theorem. So we have a homogeneous system of linear equations. And so what we have is k, which is the number of unknowns, is greater than the number of equations. And so by this theorem, so what we get is, so we get that Ax equals 0 has a non-zero solution. So this is exactly what this theorem says. So if we have more unknowns than equations, then we have a non-zero solution. But what we said here is that if we have a non-zero solution, then this implies that this set V1 through Vk is linearly dependent. Now, this corollary says, for example, that 5 vectors in F3 are linearly dependent. But it doesn't say the opposite, right? So this corollary works only in one direction. So it doesn't say that any 3 vectors in F5 are linearly independent. So if we have 3 vectors in F5, then they could be linearly dependent or linearly independent. So this only says that if we have 5 vectors in F3, then this set is guaranteed to be linearly dependent. So if you ask such a question, so then you don't need to do the calculations that we said before, right? So in this case, we can just apply this corollary and just conclude that automatically this set of 5 vectors in F3 is linearly dependent.